画面是用哦，所以我们我插错歌了吗？
没有，但另外一边不知道是什么会有。
这条是谁？
应该是
他换了一个。OK。
这种电脑的
Okay. This and 然后为什么我的作业放那就可以了。Q1 okay. I think it's time to start. So yeah, for your homework you can put in here. And but we are stop recording. Start recording. Okay. The bit rate seems fine. Okay. Anyway, yeah. Let's go back to our class. So this time. This time we once again finish the postulates of quantum mechanics. Let's review them once again. The postulates are first, every physical system there is a Hilbert space, and the state of your system is a univector unit Hilbert space. And the second postulate is that every transformation of your system is described by a unitary matrix. And then the third postulate is that a measurement on your system is described by a set of measurement operators. And when you do measurement, your state will collapse into this mi psi, and the outcome I happen with probability non-square of mi psi. And this is wrong file. Should do this one. This is this one. Yeah. Yeah. So your measurement happen with this probability mi psi of non-square, and then there is this 3.5 postulate that says when you have a composite system composed of many systems, let's say n of them h1 to, and those system has the Hilbert space h1 to hn. Then the Hilbert space of the composite system is described by this Penton product. So it's h1 tensor h2 tensor to hn. And this is why we talk about tensor product this time, this chapter. Okay, and we run through examples of quantum system. So the simplest example is a two-dimensional space. It's a qubit, and there are unitary, there are Pauli matrices, and there are measurements that are also the Pauli matrices because it's both Hermitian and unitary. Yeah. And there's a measurement problem that we talk about. Now, orthogonal states cannot be distinguished. So that's that. Okay. And so today we start with another example of quantum mechanics. This is kind of so this experiment is more important in physics class. So when physicists talk about quantum mechanics, sometimes they just start with this. because this is good evidence of quantum mechanics actually happen in our real world. So the experimental setup look like this. So there is some oven that you will heat up lots of silver atoms, and the atoms get shoot out over this hole, and there is a screen here, and because the atom shoot out and it spread out, and then you get this spread of dot on your screen as your silver atom hit the screen and deposit here. Okay, so this is like a default setup when you are doing nothing yet, and and here we want to write down the coordinate space, so the description is a little easier later. So this is x, y, z. So the y direction is the direction that silver atom is passing, and then there is x direction, the z direction that align with the two dimension of this screen here. Okay, and that was going to be useful. And so we know that, so by some physics, we know that the silver atom actually has a spin. That means that it has some intrinsic magnetic moment. So it's kind of like a small magnet like this. There is a north pole, south pole. And so when you pass it through some magnetic field, you will get, there will be some force generated from the spin and the interaction between the spin and this magnetic field. And then weird thing happen. So when we pass the silver atoms through this magnetic field in the z direction, it split into two dots. Okay. So yeah. So this is a real experiment happen. People have the silver atoms shooting out and passing through magnetic field, and it's split into two dots in z direction. And that's kind of surprising if you think about classically, because classically you have some magnetic spin, and these random silver atoms shooting out, so your spin should be in like a random direction. It can be all the 360-degree direction, and you kind of expected your dot gets stretched out, like you have a distribution over all 360 degrees, and depends on whatever degree your spin is pointing, your dot should kind of get continually stretched out into a longer dot. But that's not happening. There are only two dots. It's quite clear separation here. So actually, so this is a very quantized effect. That means that the spin actually, when you pass through magnetic field, kind of like there are only two spin directions. It's either spin point up or spin point down. There is no continuous distribution. There is only two results. It's either up or down. Okay. And yeah, so that's why people start to describe the electronic spin here by a two-dimensional space. So it's like a qubit. And yeah, a qubit that only know two answers. It's either in the 0 state or 1 state. And here 0 state corresponds to spin point up, and 1 state corresponds to spin point down. Okay, and and we think about spin as it's possible to have a superposition between 0 and 1. And yeah, so we know that for more general quantum state, it's a superposition between 0 state and 1 state. And so it has amplitude A and B, and you write as A and B. And if your atom is in some state that's described by AB, and when you pass through this z direction magnetic field, it's like doing a measurement on the on the z component of the spin, And when you do measurement, then with probability a squared, it goes up here, and the probability b squared, it goes down here. So this is a computational basis measurement. Okay? Yeah. And but no matter what proportion of these a and b is going to be split into those two dots. Okay? So maybe for some states you have more a, for some states have more b, but it's after you do measurement, it's either this dot or that dot. And yeah. And so we formulate this by saying that the spin is described by a two-dimensional space. And now this two-dimension is kind of important. It means that when you do a measurement, when you do a orthonormal measurement, the spin only answer you with yes and no. So there are only two answers the spin can answer. So this only answer yes no is comparing to this continuous dot direction. Because once again, for classical spin, using the spin direction is like a continuous variable that can be all 360 degrees. But here no, here you ask this quantum spin, then it's a two-dimensional quantum space. Then when you ask its direction, you only know it only answer you with yes and no. Okay, and okay, but now you think this is kind of weird. If you ask it in z direction, it either answer you are plus z or minus z. So what happens if you ask it in x direction? Okay. And now this is kind of sort of experiment. Means that people think this will happen, but I believe they haven't really tried out the experiment because it's really hard to do. Okay. But if you pass the silver atoms through a x direction magnetic field, it will also be split into two dots, just because there's some symmetry between x and z, and you expect this to happen. Okay, so you will split into two dots in the x direction. And what's really weird is, what if you pass the spin into z direction, and it will kind of split into two strings, right? So this dot state that get collapsed into 0, and this string state that collapse into 1. And so what happens if you take those states that collapse into 0, that we kind of classically think they are all spins that's pointing up, right? And you measure in x direction. Okay? And then we can use the calculation we talked previously to do the prediction. So the state here is this 0 ket, and when you measure in x direction, you are basically measure the sigma x operator. Okay, the sigma x operator here. And this also means that when we are doing this magnetic field in z direction, we are measuring sigma z operator. Okay. But anyway, so this part is measuring the sigma x operator. And sigma x operator can be written as projector onto x, projector onto plus state and projector onto minus state. And yeah, and we kind of already see this kind of a measurement. So your input state is 0, and your measurement operator is plus plus and minus minus. Then you measure into plus with 50% probability, and measure into minus with 50% probability. Okay. And when you measure plus, it gets projected into plus state, and plus x is probably here. Okay. And when you get into minus, it will collapse into the minus state. So it's this dot here. Okay. So you take this spin up thing, and you ask what's your spin direction in x, what's your magnetic moment in the x direction. Then you say I point up, I don't really know about x direction, so I guess it's 50-50 again. Okay. Any question? No. Okay. And here, and now we can do different concatenation. So what if we, okay, so the first part is the same. We're kind of omitting the downstream here. So you do a z measurement first, and your atoms get postulated into either 0 or 1. And what if you do take this 0 string and do a z measurement once again? Then you expect that, well, this is something spin point up, and you measure it, and it stays spin point up. So there is only one dot that's up here. Okay? And this can be explained by the mathematics we had before. So yeah, so you are doing z measurement, that's measuring the sigma z, and it's basically computational basis measurement with the measurement operator being this project onto 0 and the project onto 1. And yeah, and your input state is 0. So when you put this 0 into this measurement, you see that output is 0 with 100% probability, and output of being 1 is 0%. Okay, and once again, this is the principle we talk about. So if you repeat the same projective measurement twice, then you will get the same outcome result. Okay, and now there is something weird, really weird, when you try to concatenate 3 measurements together. Okay, so you shoot out your atoms, and then you do this z direction measurement. Then you take spin up strings, so those are 0 kate, and you pass it through x direction magnetic field. Then you take all the path string, and then you pass through another z direction magnetic field. Now, then you put a screen here. Now, what should it look like on this screen? Anyone want to try to answer? Okay. Is it going to be 1 dot, 2 dot, or something else? Okay. Yeah. Well, so here's the answer. So if we follow the mathematics, we are measuring a plus state here with sigma z, and then sigma z has a measurement operator this projector onto 0, or a measurement operator this projector onto 1, and well, then this is really the same kind of calculation. You see that the post-measurement state is 0 with 50% probability, or it is 1 with 50% probability. So you should have this 50-50 split once again. Okay. But now you think about what the atom that end up here actually goes through, then it's really weird. Right, so it goes out, and you go through a z direction magnetic field, asking it, are you pointing up or down? And it say, I'm pointing up. And then it goes through x direction magnetic field, and asking, are you pointing left or are you pointing right? It say, I'm pointing left. Is it left or right? I think it's probably right. Anyway, anyway. But the guy asks once again to this z direction magnetic field, are you pointing up or pointing down? And he said, it's really 50-50%. And but you look at here, you see that you are already selecting out those atoms that pointing in up direction, and you kind of think, well, isn't this particle already pointing up? Then why does it say it's 50-50 mixture of up and down here? Okay. And so this is my interpretation, is that the spin is a two-dimensional space, okay? And quantum state in two-dimensional space is really dumb. It only remember one bit information, kind of, right? So everything on this state is described by this two-dimensional vector. So kind of only have one bit of information. So that means that if you ask it what is direction in x direction, then you collapse into this plus or minus state. And the only thing it remember is whether it's pointing left or pointing right. And it totally forgot its information on z direction. So, so if you ask it in x direction, then this collapsing of quantum state makes the particle only remember its direction along the x-axis, and you forgot the previous information on whether it's 0 and 1. So if you ask it once again on the z direction, it's going to answer you with this 50% probability once again. And a little more physics. So I'm not sure how many of you from double E and take electromagnetic, but this is kind of what happened in the polarization of light, and yeah, and so you can do a sequence of measurement on the polarization of light, and the polarization will kind of rotate around. So if you know that, then this is similar. If you don't, then you can follow the math here. Okay. And yeah, so this is something really interesting. You kind of see that you can manipulate your state around by doing measurement in different directions. And something more about computation is that this can be made very general. There are actually ways to do every computation by just doing measurement in different directions. But that's something that we might talk about much later. Okay. So any question about this sort of experiment and the corresponding mathematics behind it? If not, well, then let's define more notations. Okay, and this. So the next thing we talk about is POVN, and POVN stands for positive operator value measure. This is really hard to understand because it's something from math, so you only need to remember the name POVN. And it's actually something easier than what we talk about. So POVN is a less informative way to describe a generalized measurement. Okay, so remember when we describe the generalized measurement, we say it's composed of this set of measurement operators. Okay, so those MI are called measurement operators, and they are matrices. And a POVN is another set of matrices that are just MI dagger times MI. Okay? So if you have a set of measurement, there is a corresponding set of POVN, where the POVN element, if there is a measurement, there is a corresponding POVN, and the POVN element EI is just MI dagger times MI. Okay. And so this lose some information about the measurement because there are different MI dagger MI that give you the same EI, but it still gives you the information you are probably most interested in. So if you are given a POVN corresponding to some measurement, then you can calculate all the outcome probability PI, because PI can be written as this psi mi dagger mi psi. So you really only care about this mi dagger times mi, and that's EI. Okay, so if you're given EI, then you can calculate the outcome, the probability of outcome I, and that's just this inner product between psi and EI. And it's this psi EI psi. And also the EI need to satisfy this completeness relationship just from the completeness relationship from MI. Okay. And but we say we lose some information about the POVN from the measurement, and the information we lost is that we don't know the post-measurement state anymore, okay? Because we don't know which MI it is, and the post-measurement state is MI psi. So yeah, so if we just write EI, we don't really know which MI gives to this EI, and we don't know this state. Yeah. But sometimes it's okay, because sometimes in some scenario you only care about the probability, then you can just write down this EI, and they are maybe a little easier to describe. Okay. And yeah, and obviously you can do this for any kind of measurement, and but for projective measurement, remember projective measurement, then those MI are projectors PI, and for projectors, PI dagger PI still equal to PI. And so for projective measurement, writing all the measurement operator and writing all the POVN is really the same thing. So it's not very useful. So usually you do this POVN description on non-projective measurement. Okay. And then we kind of do a converse of the property we talk about here. So here we are saying a measurement, you can get the POVN, and POVN obviously this EI will be positive, and you will satisfy this completeness relationship. And the converse of that is any set of operator EI, and satisfying every one of them being positive self-independent, and satisfy this completeness relationship, some EI equal to identity. If this set satisfying those two conditions, then this set is a valid POVN, meaning that you can kind of is corresponding to some valid measurement. And so there is some quantum measurement that will have this kind of POVN element that's this set of EI. Okay, so yeah. And once again, being positive self-definite, PSD means that all the eigenvalue are greater or equal to 0. And some confusion about notation is that if you read Nielsen and the Tron, it calls it positive instead of positive self-definite. But yeah, that's just some notation. Any question about POVN? It's just measurement, but with a little less description. Okay. But I guess it's easier to describe the probability, because then you don't need to do this dagger part. You just write this sandwich between psi and EI. Okay. And okay. So then let's see a little example of how the EI can help you. We describe something with simpler notation. So we describe a generalized measurement that distinguish quote non-orthogonal state. So here we are distinguishing, but not perfectly distinguishing. So what do we mean by distinguish? Is that, well, let's say we want to distinguish this 0 state and the plus state. They are not orthogonal, so we know it's not possible to have two outcome measurement where you get first outcome, you know input state is 0, and you get a second outcome, you know the input state is plus. But we can do this 3 outcome measurement. And the first measurement is has POVN element that's projected onto one scale by some number, and the second element is projected onto minus scale by some number, and the third operator is just identity matrix, subtract these two out. And okay, so this is a value POVN, and let's go back first, and anyway, yeah, let's check this value POVN first. So you want this to be a value POVN, then you need to check those two things. So every EI, so E1, E2, E3 should all be positive, and they need to sum to identity. So obviously they sum to identity because I just write this here. Okay, so by construction, sum E1, E2, E3 equal to identity. Okay. And why are they positive? Well, E1 and E2 are just a positive number times another positive matrix, so those two are obviously positive. And the third one is also positive. Basically, you need to check it. Okay. And yeah, you can do calculation, but this is some 2x2 matrix. You can check that this is positive. And something more to say is that we want to ensure this is positive. That's why we need to apply those two factors here. Because if those two numbers are too big, then E3 will be negative, will have negative eigenvalue. But we already done the math, and this is the maximum value. We can have E1 and E2 here, without E3 to have negative element, negative eigenvalue. Okay, so yeah, that's something you can check, or maybe we can do new homework here. But okay, but anyway, this is our POVN. It has 3 measurements, so there are 3 possible measurement outcomes. Okay, and then we can see the good thing about construction. So this E1 is a projector onto 0, and we know projector onto 1, and we know 1 and 0 are orthogonal. That means that when you get measurement outcome 1, the first measurement outcome, so you get the outcome corresponding to E1, then the input state must not be 0. Okay. Then there are only 2 input states, it's not 0, then it's plus. Okay. Okay. So you see the outcome 1, you know the input state is plus. And so by the same logic, when you see outcome 2, then this minus state is orthogonal to plus state. That means that when you see the outcome 2, it cannot come from plus, then it must come from 0. So E1 and E2 kind of perfectly tell you whether you are 0 or plus. When you see those outcomes, you know all the input state. But then there is E3, and there is no guarantee here. When you see outcome E3, then you just don't know whether the input state is 0 or plus. Okay? So that's why this is quotation distinguishing, because it is not perfect. There is always this chance that you get outcome 3, and you cannot say anything about whether it's plus or 0. Okay, but it partially distinguishing 0 and plus, because when you see outcome 1 or outcome 2, then you know, so you have a chance of seeing either outcome 1 or outcome 2, and you know your input state. But there is some uncertainties in kind of like error here. Yeah. And let's go back a little bit. And we see it's a useful thing. It's a useful example of this POVM formulation, because here we're only describing things in in the POVA element E1, E2, and E3. So we don't really need to describe the A11 MI. If you want to say MI, then it's really annoying. You need to take a square root of this thing. Yeah, you need to take a square root of those two are okay, but square root of this is going to be really ugly and unnecessary, because you only care about the measurement of probability, right? So yeah. So just describing the POV element make this derivation a little easier, because you only care about things like 0, E1, and 0. Yeah. Okay. And anyway, so here's another intuition here. It is that you probably see from this example that there are many different, I should say, criteria and ways you can, or protocols you can design to learn quantum state, right? So just from this example of trying to distinguishing plus state and the zero state, we come from previously we say we can, if you want to perfectly distinguish them, it's not possible. But here we say if we change our goal a little bit, we can have this yes and no and I don't know 3 answer measurement, then it's possible. So yeah, so this sort of thing is still an active research area in quantum information. And it depends on how much and what you want to learn about quantum state. So this kind of question usually start from there is a set of state. So maybe it's not just 0 plus, and there is also a minus. So you have a set of state that you don't know, and maybe there is some distribution over that. And anyway, you are given a quantum state from some set, and you want to learn something about it. And then you think about what's the optimal measurement to do that. That give you a basic success probability, depend on your metric. And those sort of questions are studied a lot in quantum information theory, and it's still an active research area. And some example of the questions are like quantum state tomography. So this is a question where the input state is really anything. There is no this state is, say, auto qubit state, and you want to do some measurement or you want to do a lot of measurement, and to learn what your input state actually is to some fixed error precision. And there is also this quantum state discrimination problem. That is more like an extension of this question. We are given a discrete set of state, so maybe 0 plus and minus. And there is also a probability distribution over them, and then you want to decide what is actually input state, and with the optimal probability. And yeah, there are more of these questions that you can describe here, and this is a really interesting research area. But well, anyway, back to the boogie example. So you have a question about these three outcome measurement to distinguishing zero and plus state? If not, yeah, let's keep going. Okay, so we kind of jumped into a different topic. But this is quite an important concept. It's the concept of phase. So, well, phase mathematically, a phase is a number, it's a complex number that has known one. So you can write it as e to the I theta for some real number theta. And well, you can multiply your phase on your state. Okay. So maybe you can have e to the I theta multiplied on phi. And and the example of phase is like -1, right? If you hopefully you remember your basic complex number theory that -1 is e to the I pi. Okay. Anyway, so the first thing about phase is that global phase does not matter. So by this I mean that if you are given you have a quantum state phi, and you think about another quantum state phi prime, that is phi applied by a global phase e to the I theta. First, this is still a valid quantum state because it has known one. And but anyway, those two states. So mathematically, those are two vectors, right? So maybe this is a -1. Then those are two vectors actually really far away from each other. But physically, they are really the same state, in the sense that you do any measurement on phi or any measurement on phi prime, you will get the same outcome distribution, same outcome probability distribution. So yeah, you can just do the calculation here. So if you have some measurement described by the set mi, then the outcome of input state psi prime. So when input state is psi prime, the probability of getting outcome I, so this pi prime, is written as this. So it's psi prime mi dagger mi. And psi prime is e to the I theta psi, and so you put in. So the psi prime, you will get the extra factor of e to the I theta here. But when you think about this psi prime bra, now psi prime bra is psi prime and apply a dagger. But remember, when you apply a dagger onto a vector or a matrix, you need to do complex conjugation. So when you do complex conjugation, this e to the I theta becomes into the minus I theta. Yeah. So you have a e to the I theta here, e to the minus I theta here, and those are just numbers, so you can put in any place, and they just cancel each other. So you get psi, mi dagger, mi psi. And that's just a probability when the input is psi and you get outcome I. And this is true for every I and any measurement set. Okay? And but remember so from the very beginning we said you have a quantum system, and you want to get any classical information out, you must do measurement. But that means if you do any measurement, you get the same outcome probability distribution. Then there's no way you can tell apart those two things, right? Because for the classical observer, you only always give the same outcome. So even though mathematically those two vectors are very different, physically they are kind of the same. So that's something really weird. But so global phase does not matter. But okay, so then this is tricky because when we do our problems, sometimes there will be this global phase, and yeah, I guess it will be. So it's better to still keep them because of the next thing. But usually when you omit the global phase, we should give you credit for your answer because the global phase does not matter. But then there is a relative phase that really matter. Okay. So an example of relative phase is here. So remember, plus state is this 0 plus 1, and the minus state is this 0 minus 1. And you can think of this plus here and this minus here as the local phase. This is a phase multiplying on your one component. So yeah. So because minus 1 is e to the I pi. E to the I pi. Yeah. And the local phase really makes a difference because after you get a local phase here, this plus state and this minus state are orthogonal. Yeah. And this is really distinguishable, actually perfectly distinguishable difference. Because you know when you do an X direction measurement, you can 100% probability distinguishing those two states. So yeah. So that's the thing about phase. Global phase does not matter, but relative phase really change your state. Yeah. Any question? Okay. If not, then let's go back to another topic. That's the composite system. So, well, we change our lecture a little bit. So we already talked about this a bit in our postulate. Our postulate 3.5 talked about when you have composite system, then you need to tensor product their Hilbert space together. And let's describe that in more detail here. So when you have composite system, then you need to use tensor product basically everything. So here is a schematic. You have a system A and a system B. System A has Hilbert space HA, system B has Hilbert space HB, and your system A is in some state psi, and your system B is in some state phi. Then you put system A and B kind of close to each other and consider what happens if they are maybe having some interaction. Then the total system is in this Hilbert space HA tensor HB. And if nothing happened yet, just this in state psi, this in state phi, then the total system will be in the state psi tensor phi. Okay, it's a product state. And then you can think about doing this more. So you have a system C, D, E, F, G. Then you just keep tensoring more Hilbert space and more Hilbert space. Okay. So for example, if you tensor together n two-dimensional system, so n qubit, then each of these systems is the individual one has dimension 2, so it can be written as C2. Then you have C2 tensor C2 tensor C2 to the n times. And the total thing will have dimension 2 to the n. Okay? Because of each time those two multiply together. Remember, the dimension of HA times HB is multiplication of the dimension. Okay? And then once again, we have this. So this is more like a reminder. So in a composite system, we can talk about entangled state. So entangled means that it cannot be written as this product. So remember, if each system is separate, nothing happens if you just consider the state of each system separately, then they are in this psi, phi, etc. And you put them together, it will be this product state psi 1, psi 2, tensor psi n. But there may be some interactions happen, and you see that this tensor product together space is really huge, and there are entangled states that cannot be written as the product of those separate states. Okay. And we are going to see example soon. Okay. So yeah, here example. The example of entangled state is this. So 1 over square root 2 O0 plus O1. Oh, okay. So we are going in weird order, but we should probably talk about the basis of those. The basis of this tensor product space first. And the good basis is a computational basis for this n qubit. And yeah, and we just omit all the tensor product, those all close here, all times here. So we'll omit all the tensor product here, and we just write this bit string. So 0, 0, 0, 0 means 0 tensor 0 tensor 0, and then there's 0, 0, 0, 1, and so all 2 to n bit string are the basis of those n qubit. Okay, so there are 2 to n bases. And the example of entangled state is the O0 state plus O1 state with some normalization. Okay, so it's time for a break. So any question? Otherwise, we'll stop for 10 minutes. Okay, yeah, let's have a break.他的速率看起来比较高。哦，然后同学可以来交作业。
算出来，他这样算那个几率，如果他算出这个几率，代表绝对不会是零的几率，就不会是那个结果。
就零的是，如果 input state 是零的时候，一定不会是一即是结果。
所以让他算出这个是4分之一，就代表4分之一的几率结果是零。
你要想一下那个conditional probability 因果关系。input 是零的时候，就是你要列一个2×3的表嘛，所以有 input 是零的时候，然后有3个几率；input 是正的时候有3个几率，然后再反推回去，会有你看到正的时候，这样写吧。我们要列一个表嘛，所以有 input 是0或是正，对吧？然后 measurement 的结果会有E1、E2、E3 嘛？
对。
然后，所以是0的时候是怎样？这个是0吧？我记得这两个是0。然后这两个是对称的，就要 P 跟 P 好了。然后再1减 P 1减 P 这样子。对吧？然后，所以这个有3个几率，然后我们是要倒推回去。如果你看到这个东西的话，那远不可能是这个，所以一定是这个。然后你看到这个东西的话，远不可能是这个，所以一定是这个。但我这样讲其实偷懒了，就是这样讲，其实我是assume说有一个一开始有抽这两个东西的几率。可能是50%这样子，这样子比较好描述。然后我们想要讲的其实是 conditional probability 嘛，其实 probability 你的 input 是0，然后 condition 然后你看到1、1这样子，然后这个有点忘记了这是怎么算的。然后这个会是这个 joint probability C1，然后再除以 P1之类的。但是这样是很啰嗦，所以我们就对，
看一下。
我们想要说什么？我们想要说，我们比较想的是这个正的东西。但是这样算没有比较快就是了。我们想算是正的，然后你发现它是100%之类的。对。我们希望这个等于1这样子。然后 conditional probability 你的 input 是0 conditional 你看到1 2，这个要等于1这样子。那直接从这标注比较快嘛，因为你 conditional 这个，那你这个会是这个平均，这个一重新normalize一下，那这里是0，那这个1会变100%，然后这0这1会变100%这样子。
所以他要么就是知道它，然后剩下的几率就是他不知道是什么的几率。
就是他知道不是这个，所以他一定是这个这样，有点逻辑推理。
了解。那3代表什么意思啊
？3就是没办法，就是你完全不知道的东西。
就是完全不知道的几率。
对啊，完全不知道。就是因为他们不垂直，所以会有这个3的东西，就你不知道的结果。
了解。OK。
这个计算需要什么程度？
就是一直做 measurement 啊。
跟直接做最后这个 measurement 这样会结果会
不一样。
不是说这个好像说只会选出来，可是到最后可是有2边都没有。
对啊，2边有。我说跟你把中间遮掉不一样，你把这遮掉的话，就是这个很奇怪，是你把中间遮掉的话。那你用0去做measure的话，就不会有2边了，因为0它只会告诉你是0的。但是你做了中间这个，它就变成2条。
那我在计算几率的时候，如果把这2个都遮掉，这样
这样子你不知道你总是要给个input嘛，然后那个之后会讲。但是这2个都遮掉的话，就等于是一开始这个嘛，然后一开始这个我们说是一般这样。但是你就要假设一下你进来的 state 是什么东西。进来 state 是什么？要到下章会讲，因为这个有点奇怪的东西。因为它是等于是 classical distribution， 然后成 state 这样。
那个东西是真实世界里放在那种
对啊，只是就是先讲后面的东西吧。就是你这里想一下的话，我们想的是出来的东西是完全随机的嘛，那就是这个完全随机的东西应该要有，你不管用什么方向去量它，你一个力不管什么方向去量它，它应该要50/50嘛。对。但是如果你去想说我们这个 AP 的话，那其实有，但是不太对，会是歪方向的。就是你想自己出来的东西，不管你出来自己方向量，它都要是50/50。但是如果是 AB 的话，就是AB 的话总是会有一个方向比较多这样子的感觉。对。那要怎样东西才会是完全50/50的？会是下一章会说是 density matrix 这样子。然后其实我们不是用一个向量，是用一个矩阵来表示。然后矩阵来表示的话，它会是一个1/2、0/0、1/2的矩阵这样子。然后 后如果你对这个东西做 measurement 的时候，你有个 mi 的东西，那样子，然后这个东西叫 rho 好了，然后这个东西你会有 pi 等于 trace rho mi 这样子。然后你就会看到说，不管你是用零啊，还是用正的啊，什么丢进去，这个 pi 永远都是二分之一，二分之一。
然后你刚刚讲那个偏正跟这个的关系是什么？刚刚有讲到后来
就是这个跟后来就很像嘛，就是会有说，会有说偏正，然后偏正量这个方向，然后你用这个方向偏正，你去量它这个方向偏正的话就上下，然后会有说，但是你去弄这个方向偏正的话，那它就会转过来一点，然后再偏正，再量这个方向偏正，它就会转过来一点，然后你可以慢慢把它转成垂直的偏正之类的事情。
哦。
对吧？
就是那个偏正偏，然后直到画。
对啊。
这两个垂直不是就黑掉？
就两个垂直会灰掉嘛，但是如果你中间再夹一块的话，它就会没有那么黑了。有这件事情吗？
哦。
然后这个就是有点像的事情，就是你本来看这个它是零的东西，然后你去说它有没有往下分量，它是没有的。但是你中间加了一个 x 之后，你就发现，它是有往下分量的。
这个实际去算这三个的那个，这样算出来是就符合这个结果。
对啊，实际算的话就会每次都是二分之一、二分之一、二分之一的，所以你就会有4分之一的机会跑到下面过来。但是如果不加中间这个的话，就是零的几率到下面过来。Okay. Okay, let's get back. So let's get to our composite system. So any question from this class? If not, yeah. So let's talk about our n-qubit system. And yeah, as we said, the n-qubit system it has its computational basis. That's the tensor product of the computational basis of each qubit, and the computational basis of each qubit is 0 and 1, and there are n qubits. So there are so those bases are described by n-bit string, and there are 2 to the n of them. And entangled state is this O0 state plus O1 state. Okay. And now let's think about state of n qubits. Okay. And the first thing you see is that this space is huge. It has 2 to the n dimension. So state on this space is a 2 to m dimensional vector. And just the information here is a lot. It's a 2 to n dimensional vector. There are 2 to n coefficients there. And there are 2 to n coefficients. 2 coefficients are complex number. But let's be a little generous. Let's say we want to describe each coefficient to constant precision. Then that requires some constant bit for each coefficient, and so you need constant times 2 to the n bit to describe one vector in one vector in this 2 to the n dimensional Hilbert space. Well, there is a little, if you want to be a little more precise, because there is a normalization of the vector need to have some square equal to 1, so actually only 2 to the n minus 1. But anyway, it's about 2 to the n bits to describe one vector here. And what about if you have n bits? If you want to describe a state of n classical bit, then that's n bit string, and you only need n bit storage. So you see there is a 2 to n versus n difference. Okay. So if you want to classically store a data on n qubit, and then that's a lot more data than n bit string. Okay. So people think this might give you exponential content advantage because it looks like this vector has a lot more information. It looks like there are exponentially more information because there is this 2 to n versus n bit. But it's not simple because now if you try to store information in this 2 to n dimensional space, then remember that's a quantum state, and you want to get the classical information out, then you need to measure it. Okay. So the very reliable data that you can perfectly distinguish, remember you can only perfectly distinguish orthogonal states. And in this 2 to n dimensional space, if you want to find the maximum number of orthogonal states, then there are only 2 to n. Okay. And so they are like also normal these computational bases, right? There are 2 to n of them, but 2 to n of those things are just n bit strings. So if you think about the information stored in these computational bases, it's basically just same as classical n bit string. So if you only store classical n bit string, well, they can be perfectly distinguished, but that's not better than, that's not better than just using classical bit. But so if you want to store other vectors, so maybe like vectors in this form, then then you get some trouble in readout because then you are starting to get some non-orthogonal pairs. So if you store data in those strings and then this entangled one, then say this O0 and this state has non-zero inner product, then you cannot perfectly distinguish them. So you see that if you really want to use this constant times 2 to the n bits of different coefficient on your n bit Hilbert space, then you get a lot of non-orthogonal states, and non-orthogonal states cannot be perfectly distinguished. So then it gets really tricky that how much information you can actually store here. Okay. And you probably see that how I describe here is kind of fuzzy. It's because this is also an active research area. So the big question here is that, now you have this 2 to the n dimensional Hilbert space, and how much information you can actually store here? Is it 2 to the n bit, or it is n bit? And once again, that depends on what precise the question you ask. So for some protocol, you can only get n bit of information out. So if you want, say, perfectly distinguishable information stored here, perfectly distinguishable classical data stored here, then that's only n bit. But there are other things that you probably don't need. That you allow some error or something, then it kind of look like this exponential bit. And That's also something interesting in quantum information theory. Kind of like, and that's related to this learning quantum state thing. So it depends on what you want to learn about the quantum state that's stored in your exponential size Hilbert space. Okay. So any question about composite system? So the bottom line is, so we talk about a lot of a lot of intuition, but the real calculation you need to do and things to remember is that you tensor product everything together. Okay? The Hilbert space is going to be tensor product together, and your state might be tensor product together, but they are going to be weird state. There are more state than those tensor product state. Okay, then let's change another topic. Let's talk about this no-Collins theorem. And this is very fundamental result about quantum information. That is, you cannot copy-paste your state. So for classical data, you have a string, then you can read your string and you can copy your string. That's always possible. You can do copy paste. But for quantum state, it's actually really weird. So if you don't know the quantum state, then you cannot copy it. Okay? Remember, quantum state is something that you need to measure to get some information out. So if you are just given a quantum state that you don't really know what it is, then it's not possible to copy it. And we write that in a mathematical form, like this. So it's not possible to have a unitary, so this is like your copy machine. And well, you want to copy arbitrary state. So let's say this is a state that you want to copy, is psi, and then there's another register that's empty. So you have a composite system of two subsystems of the same size. So one system has maybe n qubit here and another n qubit here. So you want your unitary to copy this psi onto this empty register, and it will become psi tensor psi. And here there's this kind of important restriction here. So, and we want this copying unitary to be perfect. So you want it to copy any state psi. Okay. And we prove that this is not possible if you have all state psi here. And actually, it's not possible even for just two states if there are not orthogonal. Okay. So if you have two states, psi and phi, okay, and we have this universal coupling unitary here, and obviously, just by definition, you apply on psi 0 should copy this psi, and you apply on this phi and 0 should copy this phi to phi phi. Then we just take those two equations and do inner product on both sides. Okay? So inner product on this side is will return this psi 0 to bra psi bra 0. And u turn into u dagger, and u dagger times u equal to identity. We have seen this multiple times. And then on the other side is just psi psi bra times phi phi kate. Okay? And then we do more calculation here. So remember, when you do inner product of tensor space, it's just each register do their inner product separately. So this psi will multiply with this phi, and 0 will inner product with this 0. But well, 0 and 0 is the same state, they are normalized, so this inner product is 1. So you get psi phi inner product, and on this side is psi phi inner product and psi phi inner product. Okay. So we have 3 psi phi inner product in this equation, and if we call this x, then this is the equation that x equal to x squared. Okay. then you can easily solve this. That you see this this equation has solution only when x equal to 0 or 1. Okay, pretty easy. And so what does this mean? So this means that your universal U can copy psi and phi at the same time only if psi equal to phi. So if the inner product is 1, means psi equal to phi. Or psi inner product with phi equals 0, means that psi and phi are orthogonal. And that means that they are perfectly distinguishable. Okay? So once again, two non-orthogonal states are really hard to distinguish, and you cannot copy them at the same time. So, like the intuition here, like if two states are orthogonal, then you can think them together as some classical information. Then classical information can be perfectly distinguished and can be copied. But if you have non-orthogonal state, then you get these quantum properties, and they are not distinguishable and not clonable together. Okay. Any question on what do we prove here? Not? Okay, let's keep going. Then, are we a little faster? Anyway, or maybe you are slower. But okay, then let's go to this a little annoying. Okay, this proof is a little annoying, so let's try to get a little faster. So let's go back to the many measurement formulation we talked about. So we kind of see that, well, we are trying to set up everything as a generalization of previous state. So now you probably see that measurement on some basis is a generalization of measurement on computational basis, because you can rotate your state, then do measurement, then do measurement on computational basis, then that's equivalent to measurement on your new basis. And we also kind of see that, well, actually this is not true, but because there are degeneracy. But ignoring degeneracy, then you see that measuring a Hermitian operator A is kind of like measuring on an orthonormal basis, because you are just measuring on the eigenbasis of A and assigning each label I some eigenvalue lambda I of A. And finally, we prove that this generalized measurement is actually just doing projective measurement, so kind of like doing measurement on A. And yeah, actually I think it's even easier. You can get the generalized measurement by just doing computational basis measurement, but you need to give some ancillar space and do some operation first. So maybe let's just jump here. Okay. It's easier. Okay. And this is on chapter 2.2 or 2.3 of the Neo-Centron. So what we want to say is that generalized measurement is equivalent to doing projective measurement or computational basis measurement on a larger space. So the mental picture we have is like this. So there's some quantum system here, and you want to do some generalized measurement on it. So some measurement described by those m sub m. Okay. And okay, there are too many m's here, but this is what notation we have. And then we have another ancillar system that's called M here. Okay? So it's another system, so there's another Hilbert space here. It's a Hilbert space with some size. we know the size. So the size of this Hilbert space, or the dimension of the Hilbert space here, is same as the number of measurement operator here, or measurement outcome here. Okay? So you have this ancilla system, so this help you to do the measurement. And as we say, the dimension is the same as the number of measurement. So we can write the computational basis here is those k to m. So this m kind of sync up this small m here, kind of sync up this small m. Okay. And yeah, so we want to do something on those two systems, and at the end, we will get the effect of doing this big M measurement on system Q. That means we will get outcome small n with this probability, and the collapse state on system Q will equal to this m sub n psi. Okay, so we want this happen on this system, and we probably forgot to say about this system is in some state psi. Yeah, it's arbitrary. Okay. Okay, and how we do that is so we have this ancilla system here, and we will do a two-system unitary U. Okay. So what we do is we will do a two-system unitary U, and so the system Q and M will have some interaction with each other. Then we do a measurement on M, and we will set up the U really nicely, and so that after we do measurement on M, what happened after we do a measurement on M, the outcomes, so number of outcomes, so we do computational measurement here, computational basis measurement here, so you see the number of outcome here already line up with the number of outcome here. And so those outcomes will happen with probability this, and we will see that the collapse state will be this on system Q. And so let's just talk about what we want, just how we construct this U. And basically we want U to have this property. Okay? So remember U is two-system unitary, so it acts on psi and 0 together. Psi act on this Q and M together, and we think Q start with this state psi, and M is initialized with some basic whatever state, some state 0. Okay, and we're talking about this a little weird, so this is probably m plus 1 dimension, but it's okay, it's just arbitrary fixed state. Doesn't really matter. And we want that after apply this U on those two systems, they will interact with each other, and it becomes this really special state. So it's summation over all measurement outcome M, and so big M sub small m times psi. So this is what on the first register, and the small m on the second register. And notice that this is probably a very entangled state, right? Because it is sum over m. So just if we don't look at this sum over m, then it's a product state is okay. So it is m psi tensor m, right? But then we sum over all different m. So that's many product states summing together, and very likely it's an entangled state. But anyway, let's see that if we get this state, you can kind of see that if this is true, then we kind of win. We already win because if we get this state and we measure this M system, then you will get outcome M with probability that's, excuse me, you will get outcome M with probability that's the amplitude of this thing, and that's this. And that will collapse the state into M sub n psi. Okay. And well, how do we construct this U? We basically say it's valid, so it exists. Okay. And so we want a unitary U to do this. Okay. So now we think this U is some matrix. So we want a matrix that satisfies this equation, this star equation. And we want to see, is it possible that you have something that satisfies this, but is also unitary. Okay. Well, and part of this will just be your homework problem. So we do the easier part. So this is not quite a proof, but we can check that big property of being unitary is that it preserves inner product, right? And so we want to check that if matrix U satisfies this equation, does it preserve inner product? And it's yes, because if you have U apply on some state psi tends to 0, and another state that U apply on phi and tends to 0, then you take the inner product of this thing. So then that should equal to this. So basically you have two equations. So U apply on psi equal to this, and then U apply on phi will be something similar here. Okay? And so the left hand side, these two things inner product are equal to this, and that's basically psi tensor product with phi. Right? So this goes to here. Okay? And on the right hand side, you have this thing and the inner product, the same thing with phi. And so that's this. Right. Hopefully you can read. So there is an M prime. Okay. So maybe I should. Okay, it's really hard to just draw here. So maybe I should just write down. So let's write down the corresponding equation. It will be easier. Okay. So you have a U apply on psi equal to this, and also U apply on phi 0. We'll have another summation. Let's use a different one. So summation n prime, another dummy matrix, dummy indices, and m sub n prime and phi, and this thing tensor m prime. Okay. So we have this formula and this formula because that's what you do. And we take those two things and do inner product with each other. And so the left hand side becomes this thing, and then oh, sorry, this is actually not true. Yeah. And this thing, do we have? This thing you can easily see that, so U dagger cancel with U, hopefully. Oh, sorry. Oh, why do I? Okay. I didn't do anything over here. Never mind. So this is not important, but but on the left hand side, we have those two things inner product with each other. Okay, and so you do the standard calculation, and so now you have two summation m and summation m prime, and you put things together. So the first register you have this psi m dagger m phi m dagger m psi, and you have wait, do I? And okay, I get the direction reverse, but doesn't really matter because they are real. And this, wait, sorry, just a little picky. So I have m prime down here. Okay. Okay, so I should have m prime here and m prime here. Doesn't really matter. And anyway, so m is a orthogonal basis. So this m prime and m inner product, this is delta m prime m. And basically means that it only has value when m equals to m prime. So instead of summation over m and m prime, you only need to summation over m. And and this is a number, and this summation, this number just goes out, and you just care about the first number. Then this psi summation m dagger m psi, and you use the completeness relationship of this measurement. So that's psi and phi. And anyway, so we spent a lot of time talking about this, but we see that there is preserved inner product because so before you apply U, then so this thing is equal to the inner product between phi 0 and psi 0. You can immediately check because 0 and the 0 inner product is the same. Okay. So okay. So what do we get here? We get that when we apply U on state that look like something tensor 0, then on low state you preserve inner product. But also we notice that U we only define it on something tensor 0, right? We only want U to satisfy this relationship, so we only want U apply on anything on C Q, and the 0 state on C M, it should become this thing. And that means that U apply on psi, let's say psi and 1, we don't really care what it happened. It can be anything. And for those data we care what happened, you preserve the inner product, so it looks like unitary. Okay, and so then this is your homework. I believe it's a bonus question that you can show that if that's the case, then you can extend U to actual unitary on Q tensor M. Okay, so the idea kind look like this. So you think U as a matrix, and there is some subspace. So something tensor 0. This subspace is preserving inner product. It's trace preserving. So it looks like part of a unitary, and you can extend this matrix to a 4 square matrix, and you put something here, such that this is a unitary operator. Okay. Okay, so that's a lot of talking. But anyway, hopefully I convinced you that this kind of unitary U exists. And then let's do the calculation that I can very sketchily, that after you get this kind of U, then you are done. You get this kind of U, and you do a measurement on the big M subsystem, a computational basis measurement on the big M subsystem. Then you will get a generalized measurement on the Q subsystem. And yeah, let's work all the calculation here. So we do the computational basis measurement on the M subsystem. So that's this projective measurement. You have the measurement operator PM, because then it's projective is a computational basis measurement on M. So it has those projector on small m, and it does nothing on Q, so it's identity on Q. Okay. And you can easily see that this satisfies the completeness relationship, because you sum over all small m, then that's identity tensor sum over small m, that's also identity. Okay. So those are your measurement operators, and you can calculate the probability of outcome. So probability of outcome M equal to, for your post measurement state, this thing, and inner product with the projective measurement, so you only need to write Pn here, and you sandwich it with your post measurement state. Then you write this with the star equation, and and because we have M here, so we need to give the dummy matrix variable different n, so call that M prime and M double prime. And yeah, you write everything out. So this is Pn, as we said, is IQ tensor n. Then this U thing equal to first register and sub small m double prime and m double prime, and also this thing. And okay, so what's important? What's important is on the second register, right? So on the second register, those small m double prime, and the small m prime, those are computational basis states. So they are also normal to each other, and their product are 0 unless they equal to each other. Right? It's also normal basis. That means that the summation only take value when m prime equal to m and n double prime equal to m. So we don't need summation, we just get rid of them, and you turn this m prime to m. So that's psi and sub m dagger, and times identity, so you can omit it, and m sub m times psi is the first register. Okay. So we already resolve the second register, it gives you this delta function and the summation. And that just turn all this m prime and m double prime equal to m. And on the first register, you see it's this thing. Okay. And yeah, this is what we want to have. This thing here is the probability that if you do generalized measurement and on the first system, on this Q system. Okay. So the probability is correct, and we also want to check the post-measurement state is correct. Okay. So what's the post-measurement state? It's this thing, right? So PM, this is your measurement operator, and the state after you do the unitary. Okay. And well, the state look like this. So obviously you do projection on M, then you only select the M element, right? So you do projection on N on the second register, then it becomes this. So on first register is big M sub N psi, and your tensor product with this small m here. Okay? So M part is this thing, and this is the Q part. And there are some normalization down here, we don't really care. It's this probability square root. And now you see this is a product state. So on Q part is this n sub m psi, and on the m part is this m. It's a tensor product thing, and that means you can kind of look at it as two separate systems because there is no entanglement. So if you only look at the Q part, then it's this m sub m psi with the normalization, and that's what we want. Okay. So summary: to do a generalized measurement, you can get it by doing some computation and computational basis measurement. So first you need to have an NC-lab register whose dimension is the same as the number of outcomes, and then you need to do this computation step. So you need to apply this really weird unitary U that we haven't really talked about how to construct, but we say it exists. Okay. And this U will depend on the measurement you want to do. Okay. Yeah, so U depend on your set of M. As you can see here, U depend on M, big M. And then you measure the record register M in the computational basis. Then the effect it will be you do the generalized measurement on your Q system. And maybe you can throw and see that it's now in some computational basis state. Okay. Any question about our derivation of generalized measurement? I guess you don't really apply this formulation, but it's nice to see this thing and get yourself more familiar with this tensor product structure, where you do measurement on one part and you think about the post-measurement state on the whole system, etc. Okay. If not, then okay, I think we are really fast. But let's talk about some kind of application. So before we talk about quantum algorithm, let's talk about quantum communication. And yeah, so this is kind of one of the answer to how many information a qubit can hold. And in this scenario, the answer is 1 qubit means 2 classical bits in some sense. So what happened here is we have a communication setting. Okay. So we have Alice and Bob. And now we have a very standard task Alice and Bob want to do. Alice want to send some classical string to Bob. Okay, so just 0 and 1. And now the question is, if Alice can send the quantum state instead, then if Alice send 1 qubit, then how many classical bits can she pass to Bob? And we see that in superdense coding, Alice can send 1 qubit to Bob, and Bob will be able to perfectly decode all 2 classical bits. Okay? So that's why it's called superdense coding, because you have this factor of 2. But there is a catch. It's just sending 1 qubit is not enough. They also need to have this idea of shared entangled state. So they need to consume a pair of shared entangled state. And the shared entangled state is going to be this form. It's very famous, called the Bell state or EPR pair. Okay. The state of the form psi equals square root 2, 0, 0 plus 1, 1. And the 0, 0 and 1, 1 means that it's a 2 qubit system, but Alice is holding 1 bit and Bob is holding another bit. And the first bit is so the first bit is 0, second bit is 0, or first bit 1, second bit 1 in a quantum superposition. So the idea is kind of Alice will, so someone, maybe Alice or maybe some referee. Okay, in this way, here we think about Alice prepare this locally. So she has some quantum computer, she compute this 0, 0 plus 1, 1, and it's a 2 qubit state, 2 qubit entangled state. And Alice can send 1 bit to Bob. Okay, so this is before she send the classical string. So this is how they create a shared entangled state. Okay. So Alice creates this entangled state locally, then she sends 1 bit to Bob. And assuming that they are assuming they have very good quantum system, so the state doesn't change at all when Alice sends this 1 bit to Bob, then this 2 bit will still in this 0, 0 plus 1, 1 superposition state. And this is well, kind of weird, but kind of not weird, but kind of weird state. So why do I say this? So you see that this thing is a quantum entangled state, and Alice and Bob can physically be really far away. Okay? But we think it's physically possible that this entanglement just get preserved after Alice sending 1 bit to Bob. So even if they are really far away, those 2 bits, they are not interacting with each other anymore, but they are still keeping this entangled state. And it's an entangled state means that it's not a product state, and that means it's not something you can prepare locally. Means that if you start with 2 qubits, and you can rigorously prove this. So if you start with 2 qubits, so Alice wants 1 qubit here and Bob with another qubit here, and Alice prepares on state here, Bob prepares on state, then it will be like some psi tensor phi, right? And you're probably already doing homework. You see that this is the entangled state, so this is not some psi tensor phi. So this state cannot be prepared separately. It must start with some interaction and you send out. And it's still stuck in this kind of state prepared from interaction. Okay. And okay, so that's a little weird, but you can also think it's not so weird because it's kind of like a classical random variable, right? If you just think it's 0, 0 or 1, 1. That's like if you do a coin flip locally and someone write down the answer of 0 and 0 or 1 1. The coin flip can be 0 or 1. And someone else write down the answer, cover it up, and maybe seal the answer in envelope and send the two envelope to Alice and Bob. Then that's some classical random variable, correlated classical random variable, either in 0 0 or 1 1, right? So that also have this long range correlation, but it's still weird because we are going to see, probably not today, but maybe next time, that this quantum entanglement is more than classical random variable. Because if this is just a straight randomness, so a coin flip 0 and 1 1, then you cannot use this to assist yourself in sending information. Alice and Bob share this straight randomness, but Alice send 1 bit to Bob. That's still only 1 bit. This sharing entanglement don't let you send in any information. But next time we are going to see that if you share this entanglement, then it's possible for Alice to do this super dense coding, such that she send 1 qubit to Bob. Then they can do something with this entanglement, and Bob can learn all 4 possible messages 0 0 0 1 1 0 and 1 1. Yeah. So yeah, this entanglement allows you to do super dense coding, and we are going to see that next time. And we are also going to have another homework set all today or soon. Yeah. Yeah, any question? Otherwise, that's it for today. Okay, let's stop.